2.3, graphs that enlighten and graphs that deceive. Key concepts. We are going to introduce common graphs that foster understanding, discuss some graphs that are deceptive, and talk about technology just a little bit. Dot plots are the first thing, and this is one that you've definitely seen before. It's a graph of quantitative or numerical data in which each data point or each data value is plotted as a point or dot above a horizontal scale. It looks an awful lot like a bar graph, except instead of bars, we've got dots. Each dot represents one instance of that number. So features of a dot plot, it displays the shape of the distribution. So sometimes you can tell if it's like a bell-shaped curve, you know what I'm saying? It's usually possible to recreate the original list of data values. So if you look at these points, I can see that the first number is 40, and the next number looks like it might be 42. And then I've got 50. Actually, there are two 50s, right? So if I wanted to, I could go through and list out every single instance of a number. I don't want to do that because it's going to take me all day because there's so many points, but we could tell each individual number there. That is opposed to last week when we talked about a frequency distribution. The frequency distribution said there were 11 occurrences between 170 or 75 and 124, and we didn't know what those numbers were. We just knew that there were 11 of them between that range. So we can tell exactly what's what on this dot plot. Stem plots, or stem and leaf plot, represents quantitative data, that's numbers, by separating each value into two parts. The stem, such as the leftmost digit, and the leaf, such as the rightmost digit. I think this is a little bit tricky to look at. It looks confusing just because of the way it's laid out. When I think about stems and leaves, I think about plants, or in math, we talk about tree diagrams. And so if you think about it, this first four right here would be the stem. Think about a tree diagram. And then it's going to have a leaf of 0 and a different leaf of 2. That's a stem and a leaf. I think maybe it's easier to understand as a tree diagram, but that's representative of 40 and 42. Remember a second ago when I listed those numbers? And the first number was 40 and the second number was 42. And then there's going to be a 50 and then another 50 and then a bunch of 52s. So I guess it's trying to eliminate extra writing. There's no point in writing that 5 all those times. And there's no point in writing 60, 60, 60, 60. So they're trying to, I guess, reduce space here. But again, you're going to be able to see all of the numbers here. It shows the distribution of the data. It's weird because it's sideways, but it's showing you the shape. You can see there's mostly the most numbers are in the 60s, it looks like. Retains the original data values, which means we can see them or list them. And one thing that's good, I think, is the sample data are sorted and arranged in order. Time series graph. Graph of time series data, which are quantitative data that have been collected at different points in time, such as monthly or yearly. So you might call this a line plot, I guess, but it is talking about times. And one feature is it reveals information about trends over time. In this, does it appear in the long-term trend? Does it appear like it's trending up or down? I can't tell. To me, it kind of looks like it's trending down. If you kind of think about it, and I mean, we've done, or you've done, linear regression in the past, so we're not trying to come up with a line that goes through it, but it kind of looks like this is trending down. One real-world application, if anybody invests, like here's kind of the price of Bitcoin all time, and if you look at this graph, from like way back in 2015, the price of one Bitcoin was $342, but here at its highest point, it's, I don't know, in the 60s. I can't, there we go, $69,000. So it's gone up from 400 and whatever that was, 423 or something, to $69,000. It looks like it's trending up, but you can change. What's kind of cool about this is you can change it from all time to this is just 1 year, and you can kind of spot some trends if you nail it down. If you just look over the past month, that seems to be trending down, right? So we can tell, we can see some different trends with a time series graph. Bar graphs. Graph of bars of equal width to show frequencies of categories. Qualitative data. Okay. Qualitative is not numbers. Okay. Quantitative, we've seen that word a couple of times already. Quantitative, like quantity or number, but this is qualitative. And if you look at this bar graph, these are not numbers. They're like categories, right? Categories or words or something that you wouldn't really think of as numbers. The bars may or may not be separated by small gaps. I think it's kind of weird to think about the gaps. We had something in the last lesson. We talked about histograms. And in a histogram, you had all the bars sitting right next to each other. There weren't any gaps in between. But here, they're saying we can have some gaps in between. So that's a bar graph. A Pareto chart is like a special kind of bar graph. It is a bar graph, but it's got the added stipulation that the bars are arranged in descending order. So that's really it. That's really the only thing that makes this different than a regular bar graph. A bar graph, it doesn't have to be in descending order. This one, it will be in descending order. This Pareto chart shows the relative distribution of categorical data, so it's easier to compare for different categories. Draws attention to the more important categories. So, this is the highest, jet ski. But one thing that's good about a bar graph, or in this case the Pareto chart, is it does actually show the data. It looks like it's clocking in just under 1,400 stolen boats. Okay, stolen jet skis. All right. Pie chart. We've all seen pie charts. Very common graph that depicts categorical data as slices of a circle, in which the size of each slice is proportional to the frequency count for that category. Shows the distribution of categorical data in a commonly used format. So here we can see the same information about the stolen boats, but they're going to say we like bar graphs better. We like the Pareto chart better. Now this one shows that jet skis was the most. We can see from either one that jet skis is the most, but the reason we like the bar graph better is because we can actually see this data. It actually shows the data. And so there's going to be a question about this, and we don't like the pie chart because it doesn't show the data. It's pretty much what they're going to ask you. Frequency polygon. Graph using line segments connected to points located directly above class midpoint values. I think that's really hard to read. All right, so let's read it again. A graph using line segments connected to points located directly above class midpoint values. All right, if you're like me, that's really hard to understand. And it's hard to make heads or tails of that. And so when you're talking about a frequency polygon, you have to go back and think about the frequency distribution. Okay, it looks an awful lot like the time series graph. Obviously, we're not talking about time. Well, I guess we are. It's not the same thing as a time series graph, but think about the frequency distribution. This example is talking about the McDonald's lunch service time. And we did an example about that last week. And the frequency distribution looked something like this. There were some times between 75 and 124 seconds, and there were 11 of them. And then between 125 and 174, there were 24 of those numbers. And so I'm not going to finish the chart or the distribution, but that's kind of what it started as. And so basically what we're doing to find this number, 99.5, we're finding the midpoint of 75 and 124. And so instead of, how else would we be able to graph 75 through 124 with a frequency of 11? So what they've done is they've said, well, here's 11, right? That's about 11. And we'll just graph it at the midpoint of that class. That's what that says. A graph using line segments connected to points located directly above class midpoint values. Class midpoint values. So then the next one, guess what the midpoint of this is? Well, 149.5, and there were 24 of them right there. All right, so I think that's a little bit hard to understand. I don't know how useful that would be. It's only useful if you're talking about a frequency distribution. Frequency polygon is very similar to a histogram, but it uses line segments instead of bars. So we very easily could have drawn a histogram just like we did in the last lesson. A variation of the basic frequency polygon is the relative frequency polygon. Remember, when they're talking about relative frequencies, they're talking about percents. And so here was the other example we did about Dunkin' Donuts and McDonald's, but now we're talking about percents here. All right, now we've gone through a bunch of different graphs that you might see, but we haven't really talked about why they could be deceptive. So graphs that deceive. Non-zero vertical axis is a big one. Non-zero vertical axis. A common deceptive graph involves using a vertical scale that starts at some value greater than 0 to exaggerate differences between groups. If you keep your eyes open, you might see this one, like in a newspaper or an article or something. And it has to do with not starting at 0. Okay, non-zero vertical axis. By starting at 10% as opposed to 0, it really skews the data, and it really gives you kind of a false impression of the difference between these two. So this graph says the percent of people experiencing nausea from using a drug called OxyContin or a placebo. You guys know what a placebo is? Placebo is like a fake pill that doesn't really do anything. You just give it to somebody and kind of trick them into thinking they don't know if they got real medicine or not. And so they do this in studies. They'll give one set of people the actual drug and another set of people the placebo, just to see if they can really tell what were the effects of the drug. So this first graph sure looks like OxyContin causes way more than double. But if you look at this one that starts at 0, it appears that it's about double. Doesn't it look like it's more than double in this graph? That's deceptive. You'll see every once in a while people will do this on purpose. But that's one example of graphs that deceive. Always examine a graph carefully to see whether a vertical axis begins at some point other than 0 so that differences are exaggerated. Next one is pictographs. I think this one's kind of weird. Drawings of objects are called pictographs, are often misleading. Data that are one-dimensional in nature, such as budget amounts. So one-dimensional means like just a list of numbers. Are often depicted with two-dimensional objects such as dollar bills, or three-dimensional objects such as stacks of coins, homes, or barrels. It says, by using pictographs, artists can create false impressions that grossly distort differences by using these simple principles of basic geometry. If you look at this pictograph down here, in 1970, it says 37% of US adults smoked. In 2013, 18% of US adults smoked. Okay? That number is roughly half. Okay? 36% is twice 18%, right? It's roughly half. So you should expect the picture to look like roughly half, but that's not the case. This first cigarette looks way bigger than twice as big. Don't you think? Okay. So what it says here, when you double each side of a square, its area doesn't merely double, it increases by a factor of 4, right? Area increases by a factor of 4. And then similarly, when we talk about volume, increases by a factor of 8. All right, so there's going to be something that talks about volume and area and how misleading that can be. When you draw pictures to represent a list of numbers, you can skew the data or just make it look completely different than what you intended, or maybe you did intend it to be deceptive. So in general, area and volume are going to be bad for us. Concluding thoughts. In addition to the graphs we've discussed in this section, there are many other useful graphs, some of which haven't yet been created. The world needs more people who can create original graphs that enlighten us about the nature of data. I don't know if you've ever played around with Excel, but you can do a lot of these graphs on a spreadsheet program. You can do a lot more things on a spreadsheet program. But anyway, I've shown you some of the main ones that will come up. In general, when making a graph to display information, for small data sets of 20 values or fewer, use a table instead of a graph, all right? Remember from before, small data sets are sometimes bad anyway. Remember, sometimes if you have too small of a data set, it's not going to show anything conclusive. It's not going to reveal the important characteristics that you would need to see. You know, if I picked 2 students and calculated their average on the last quiz or whatever, and that average was 99%, okay? Do you think it would be deceptive of me to say my class average on tests and quizzes is 99%? Probably, because that's not a big enough sample size. I need a much larger sample size to get a good feel for what the class is doing. So too small of a data set is going to be problematic, but it says for 20 or fewer, use a table instead of a graph. Graph of data should make us focus on the true nature of the data, not on other elements such as eye-catching but distracting design features. By the way, do you remember what the graph was called when we drew a picture of it? Pictograph. Picture, pictograph. So that's kind of what they're talking about there. Do not distort data. Construct a graph to reveal the true nature of the data. Then they say almost all of the ink in a graph should be used for the data, not for other design elements. And I think they're specifically talking about a pie chart. You know, the pie chart's fine, but all the ink they talk about it is wasted on this eye-catching design, I guess, but they don't really give you any of the data. And so so use your ink to talk about the data, I guess. And then also another thing that comes up in the assignment, A graph, just because you draw a graph isn't going to cancel out bad sampling. Okay. If you've got bad numbers, bad data, bad methodology, you can't just draw a picture and expect that to be okay. So a graph can't cancel out bad sampling.